Okay, there's a related calculation that we do that gives us a little better information than the average deviation. Here we found that the average deviation of this distribution is somewhat greater than the average deviation of this distribution, meaning that the numbers are on the average closer to the mean for this distribution than they are for this one where we've cleared out the middle. Now there's what's called a standard deviation, and some people ask, why would we do a standard deviation when we've got an average deviation? The best answer I can give you right now, and really probably about the best answer I can give you, because the roots of the reason go much deeper than we can go in this course. You have to have a very solid foundation in calculus before you can begin to understand why the standard deviation works better than the average deviation. I'll simply say that it's more compatible, or the standard deviation has very profound and significant meaning related to the bell-shaped curve, the normal curve. And you've heard of the bell-shaped curve. This is what works with the bell-shaped curve. This doesn't quite work with the bell-shaped curve. So that's the best answer I can give you why we would do a standard deviation, but let's see how we calculate it. The calculation is actually fairly simple. I'll tell you what the standard deviation is, and of course if you were in class you've already worked it through, and if you've worked through the document, and if you're trying to work ahead of me as you work through the document, you'll know this anyway. But the standard deviation is the square root of the mean of the squared deviations. Very simple statement, but maybe a little hard to interpret. So let's see what that means. Okay, first of all, we got deviations. We know what deviations are. Now we got squared deviations. Well, we don't really have to read any further than just reading the word squared deviations. Let's square our deviations. Okay, well, when I square these deviations, now this 8 and this one, most of these are fairly approximate, so I could be off by a little bit, but we get the idea, and they aren't off by all that much. The approximate square of 2.83 is 8, of 1.83 is 3.7, etc. 4.17 squared is about 17. Between 17 and 18, but I think closer to 17. In any case, when we add these up, we get 31. And when we then, well, that's the sum of the squared, well, okay. These are the squared deviations. Let's go back to the, I'm getting ahead of myself. Let's go back to the statement. Now, the next thing we see that modifies the word deviations, squared modifies it, mean of the squared deviations. The mean of the squared deviations we get by adding them up and dividing by 1, 2, 3, 4, 5, 6. 31 divided by 6 is 5.13. So now we've got the mean of the squared deviations. The standard deviation is the square root of the mean of the squared deviations. So the square root of the mean of the squared deviations is the square root of 5.13, which is 2.3. Now, there's this thing about a modification here. We'll talk about that in a minute. We do the same thing over here. We've got our deviations. We square them. We add them up because we want the mean of the squared deviations. First thing we see is we want the squared deviations, so we square them. We add them up so we can calculate the mean. We divide by the 6, and in this case we get 6.9. Okay, so there's the mean of the squared deviations. Standard deviation is the square root of that, which comes out close to 2.6. Now, a couple of things we'll note. Again, we see that the standard deviation here is 2.6. Here it's 2.3. The fact that the standard deviation is greater here than here is again an indication that this distribution is more spread out than this one. Not a lot more spread out, but certainly a little more spread out. And that confirms what we found from the average deviations. But let's notice that the standard deviations here actually come out a little bit closer to each other than the average deviations. 2.6 differs from 2.3. but 2.5 differs from 1.83 by a lot more. So there are some differences in the interpretations you get if you do more advanced things using average deviations versus standard deviations. Now there's one more twist to the calculation of the standard deviation. Okay, actually I'm kind of lying to you with this statement and with this calculation. Still, this statement and this calculation are useful. It gives you the general idea of the standard deviation. This word mean, I'm going to put quotation marks around it because it's not really supposed to be a mean when the distribution is this small. If you have fewer than 30 numbers, so we have only 6 numbers, so we have less than 30 numbers, and if that's the case, we make the modification that when we divide the sum of the squared deviations, we divide it by 1 less than the number of numbers. Okay, so we have 6 numbers here. Instead of dividing by 6 as we did here, we divide by 6 minus 1 or 5, and we do that here, and we get a slight difference in our standard deviation. Okay, we divide the 31 by 5 instead of dividing it by 6. And then we take the square root of that result, and the result comes out a little bit higher. And we did the same over here, dividing the 41.5 by 5 rather than 6. We get a standard deviation of 2.9 instead of 2.6. Now again, the reason for that is again very deep. The rule is simply, if you got fewer than 30 numbers, you make this modification. And the reason, as best I can tell you right now, is that it works better with the normal curve model, the bell-shaped curve.